I'm going to do two simple problems in the related rates section. This is a new topic for us. It's a big topic. It's a very important kind of word problem that we can do with calculus, especially now that we have the chain rule, and the chain rule is indeed the key thing to it. I really can't improve much on what they say in the first couple pages of this section, so I highly recommend you read that first before you watch this. But I'm going to start by doing number 2 on page 260. And I'm going to start by looking at B, because that's really the word problem part of it. We've got an increasing circle. And so if I look at stages of it, here's what it starts with. It gets bigger, and it's an oil spill. What they say is, suppose that oil spills from a ruptured tanker, which is right here, spreads in a circular pattern, if the radius of the oil spill increases at a constant rate of 1 meter per second, so that each second it's getting 1 meter bigger in radius. How fast is the area of the spill increasing at a certain time? And in fact, what they say is when the radius is 30 meters, how fast is the area of the spill increasing? So we're at some later time where this radius is 30 meters, and then if I wait 1 more second, it's going to be 31 meters. And I'd like to figure out how fast is the area of the spill increasing. That's going to be important if I'm going to try and clean it up, for example. So, my circles are just amazingly good, aren't they? Okay, so what we know is, and this is what always is true about a related rates problem, we're given the rate of change of one quantity. The radius is increasing at a rate of 1 meter per second, a constant rate of 1 meter per second. And so that means dr dt equals 1. Here we're using the d by dt notation because we're going to have a bunch of variables sometimes. There's at least 3 variables in any related rates problem, and sometimes 4, maybe 5. And we're going to really have to keep track of those, and we have to really make sure we know exactly what the derivatives are that we're taking. If we just did r prime, it might be a little bit confusing. Okay, it wouldn't kill us, but it's good to use the dr dt notation. It emphasizes that the derivative we're taking here is with respect to time. It's a rate of change with respect to time. And what we want is not something about how r changes. That's given. We want the rate of change of the area. Okay, and that's the typical setup for a related rates problem. Some rate or rates, perhaps plural, are given, and we want the rate of change of some other but related quantity, hence related rates. The key to any related rates problem is what you like to call the master equation. It's going to be some equation that always relates the two quantities. That is a universal relationship that's true at all times between the two quantities. And here, it's the area of a circle. So A is pi r squared. Now, here's where the ideas of the chain rule and implicit differentiation come in. We're going to take the derivative of both sides of that equation. And now we're going to take the derivative with respect to t, because we want to figure out rates of change with respect to time. And so it's a little bit like implicit differentiation, but here we're actually taking the derivative not with respect to a or r, not either of the variables that are explicitly present in the equation. We're actually taking the derivative of both sides with respect to t. On the left-hand side, I just get dA dt. I'm not trying to look for the answer yet. You might say, wait, I wanted to get this, and then I'm writing it down. Isn't that circular? Just like implicit differentiation, the point is I'm going to write down a true equation about dA dt, and I might be able to solve that equation, and we will be able to solve it. Over here, it's pi times r squared, and now here again it's crucial that I'm differentiating with respect to t. I'm not differentiating with respect to r. If I did, I'd just get 2 pi r. But r here is some quantity that changes as a function of time. I don't know exactly what that function is, but I just know what its rate of change is. But it is a function of t, and so this is really a chain rule calculation in disguise. It doesn't look like it, but it is. Just like in implicit differentiation problems, this is really the function r of t, then inside the square function. So you get the pi, come along for the ride. You get 2r, so I'm going to put the 2 in front. So the derivative of something squared is 2 times that something, and then times the chain rule. And so the chain rule is absolutely crucial to every single related rates problem, because it's always going to come up. You're always going to have something involving quantities that aren't t, like r is not the quantity t, it's related to it, but it's not t, and you're taking the derivative with respect to t, and that means the chain rule is going to come in. So this is a relationship between the rates. I know dr dt, that's given. That's equal to 1. And then if you just tell me r, I'm going to be able to figure out dA dt. So, if you look at the statement of the problem, this is on page 260. I don't know if I said that. If you look at the statement of the problem, it says, how fast is the area of the spill increasing when the radius is 30 meters? Haven't had to use that yet, but now that's very useful. So now I've got everything I need to know to finish the problem. dA dt is going to be 2 pi times 30 meters times, and I should have put the units in here to be really careful. That was 1 meter per second, and that's 1 meter per second. And so I get 60 pi meters squared per second. Does that sound like the rate of change of an area with respect to time? Yes. The rate of change of area with respect to time is always going to be units of area, which is meters squared, over units of time, which is seconds. So that's a simple example of a related rates problem. It doesn't bring in all the complexities that can come into the problems, but it's a simple example. It's a good starter. Now let me do one it's like one in the book I just made up a little bit on my own. Just to focus on the mathematical issues a little bit, and not so much the word problem and setup issues. Both the math and the word problem issues are important here. Suppose I have this known relationship between three quantities x, y, and z. Just let's not worry about why we would know that in a word problem context. Suppose we know that's a true fact, and I'm given that dx dt equals 5, and dy dt is minus 3. So one thing to note is that x is increasing as time goes on, and y is decreasing. And those minus signs, in increase and decrease, is one of the big pitfalls with this, is that if you don't pay very close attention to words like increase, decrease, up, down, bigger, smaller, you're going to miss signs like that. So, but just suppose that mathematical information is given. And the question is, what is... This pen is getting kind of lame. Let's switch to black. What is dz dt when x equals 2 and y equals 2? So hopefully it seems a little bit like the previous problem. I've got quantities that are related by equation that's supposed to be always true. And I've got given information about the rate of change of two of the quantities, like I had r information, or drdt information, and I want rate of change of the other quantity. Let me see if I can fit this in the next 2 minutes. Always, what you do with the master equation there is you differentiate both sides. Derivative of z to the fourth respect to t is, well, that's derivative of something to the fourth, which is 4z cubed, but then the chain rule says you've got to put in dz dt. Derivative of something cubed is the 3 times that something squared, but the chain rule is active here too, times dx dt. This is 2 times mystery function y of t squared, so we get 4y dy dt. So I've differentiated the master equation. Once you do that, you're ready to plug in any numbers that are given. You never plug in the numbers before you take the derivatives, because if you make variables into constants and then take derivatives, they're going to be 0, and that's going to be false. So I have values for almost all of this stuff. X is given as 2, so that's 12. Dx dt is 5. Y is 2, so that's 8. Dy dt is minus 3. And dz dt is what I want to solve for, so that's okay to leave in there. But then what's z? That wasn't given. Always, when you're stuck on that, go back to the master equation. Okay. Z, the mystery z to the fourth is 8, 2 cubed, plus 2 times 4. So z actually was equal to 2 as well. You go back to the master equation when you're stuck in that situation. So this is actually, z is 2, this is 8, this is 32. And so dz dt, 60 minus 24 is 36 over 32, which is 9/8. I think I did the algebra right. I was kind of in a hurry. Okay, that's a good place to stop, though.